All right. So let's take a look at these. I just wanted to do some additional examples. So here we have QRST as a rectangle. The measure of angle TQX is 70 degrees, so I'll go ahead and put that on the diagram. TQX is 70. And the length of QT is 5. And the length of RT is 13. Now, because RT is 13, I'm going to go ahead and say that each of these is 6.5, because in any parallelogram, the diagonals cut each other and the diagonals bisect each other. That's true for any parallelogram. All right, so let's start finding angles. If this angle is 70, because this whole angle is a right angle, this angle has to be 20. And then by alternate interior angles, this angle here at S would be 70, and the other angle at S, will be 20. Now, I also know that RS is 5, and frankly, that's the low-hanging fruit. There's nothing new about that. That's just like any other ordinary parallelogram, right? But one thing that's special about a rectangle's diagonals is what? They're congruent to each other. So if both of these are 6.5, both of these are 6.5, which means we've got little isosceles triangles here. Whether it's a rectangle, a rhombus, or a square, you're always going to have isosceles triangles. Yes, ma'am?
If they're all isosceles, then doesn't that mean like angle SRX is also 70?
Yes, absolutely.
And then angle QTX is also 70?
QTX, yep.
And then QRX is 20, and then
QRX, yep.
STX is 20.
Absolutely. Very good.
Oh.
All right, we only have the angles where the two diagonals meet to find. How can I find those? How can I find those without doing any subtracting?
Oh, you. Wait, what are you trying to find here?
These angles here in the middle.
So 70 plus 70 makes 140, which means that angle QRX is 140.
Wait a minute, not QRX.
Wait, QXR.
QXR, there you go.
My bad.
Yeah, no problem. That's 140. Remember that the exterior angle is equal to the sum of the two remote interiors. So this is 140 also. And then 20 plus 20 is 40. So these angles are both 40.
Makes sense, makes sense.
All I have left to do is find QR and TS, and both of those are part of a right triangle. It can get a little overwhelming when you're looking at these, so sometimes it's not a bad idea to just draw, okay, this is that triangle. I know this side is 5, and I know all of TR is 13. Hopefully looks familiar to you.
It's one of those things.
One of those things. Yes, it is one of those things. What are those things called?
Triple.
Pythagorean triples. And what is the other number? 12. Very good.
I was gonna say 8.
It can't be 8, because if it was 8, you wouldn't have a triangle. And the reason I know that is because 5 plus 8 is 13. Yeah, it's got to be bigger than that.
Whoopsies.
All right? So sometimes you're going to be using Pythagorean theorem. Let's take a look at this rhombus problem. Here, ABCD is a rhombus, and the measure of angle DAB is 120 degrees.
Dab.
And the length of DB is 40. Well, that means each of these is 20.
How do you know that?
The diagonals in any parallelogram bisect each other. They cut each other in half.
Just 40 divided by 2. I didn't read the given.
It sometimes helps. All right. Now, unlike a rectangle, where the angles that are right next to each other at the vertices are not equal to each other, in a rhombus they are. So these angles are both 60. And where a rectangle has right angles at the vertices, where does a rhombus have right angles?
In the middle.
In the middle, where the two diagonals intersect one another. These are all right angles. So, what kind of a triangle are all those little triangles?
30, 60, 90.
They got to be 30, 60, 90. You've got 90 and 60. That means these all have to be 30. That's not true in all rhombuses, but it is in this particular one. Sometimes you'll have 30, 60, 90 triangles and rectangles. Sometimes you won't. All right, so now what do I do? Which side of the 30, 60, 90 triangle do I have? Let's say I'm looking at AEB, for example.
The long leg.
Yeah, I've got the long leg. What do I have to find next?
The short leg.
The short leg. How do you find the short leg? Divide by the square root of 3. Yeah. This doesn't come out to be very nice, but that's okay. So that's 20 squared roots of 3 over 3. Not much we can do with that. And since the diagonals cut each other in half, they bisect each other, this is also 20 squared roots of 3 over 3. And then in the 30, 60, 90 triangles, what do we do to the short leg to find the hypotenuse?
Times 2.
Yeah. So this would be?
40 square root 3 over 3.
Yes. And in fact, since it's a rhombus, all of those have to be 40 squared roots of 3 over 3.
How'd you get that?
I multiplied the short leg times 2. 20 squared roots of 3 over 3 times 2 is 40 squared roots of 3 over 3.
Oh, you just multiply the top?
Yes.
Oh, I was thinking,
That you would multiply top and bottom?
yeah.
But if you take 20 squared roots of 3 over 3 times 2 over 2, are you really multiplying by 2?
No,
What's 2 over 2 equal to?
1.
1.
You're right.
That's why I get the big bucks. Oh, wait a minute. I'm a teacher. All right, and then one more example. Here we have that WXYZ is a square, and they give you the length of WY is 24. I want you to find all the angles and segments. The angles, you should be able to go through this in about, 4 seconds and get all the angles.
Oh.
Because they're all either going to be 45 or 90. Takes longer to write it than it does to say it. That took me longer than 4 seconds. And then it tells me the length of WY is 24, so what else do I know?
That each half a diagonal is 12.
Yeah. Each piece of a diagonal is going to be 12 then. And then in a 45, 45, 90, what do we do with the leg length to find the length of the hypotenuse?
Multiplied by the root of 2.
Yep, multiply by the square root of 2. So all the sides are 12 square roots of 2.
That's it.
We've got them all. Squares usually don't take very long, or at least shouldn't. All right. Your favorite words?
Worksheet.
I have a worksheet for you.